Okay, so for this question, uh, we're gonna look at is that is an Arene question. So let's take a look. So phenyl ethene undergoes a reaction with BrCl producing X. So in this case, we have to identify which one is the nucleophile and the electrophile. So we see there's a benzene ring that is of high electron density as well as an alkene bond. And then we see the electrophile being BrCl. Okay, how we know BrCl is an electrophile is that uh, chlorine is more electronegative than bromine, and bromine will possess the partial positive bond. Sorry, the partial positive charge. So you can see right here, this partially positive Br will be electrophilic and will be attacked by the nucleophilic pi bond of the alkene. And this pushes Cl to form the Cl ion as well as the carbocation being formed. So another thing to take note is that we also see that there's no use of a catalyst right here. That's the reason why I didn't use my benzene ring to attack the electrophile is because without the use of the catalyst, our conditions are actually milder. So when our condition is milder, you remember I say benzene ring is actually less nucleophilic compared to the alkene. So if it's less nucleophilic to if the benzene ring is less nucleophilic compared to the alkene group, that's why we use much more harsher conditions if we want to undergo electrophilic substitution of benzene ring. Okay, so if I don't have the use of catalyst, so my benzene ring will not undergo electrophilic substitution as readily compared to the alkene. Okay, and the purpose of the catalyst is usually to generate a stronger electrophile for the benzene to react with. Okay, another thing is that uh, the carbocation will be formed. So you can see the carbocation can be either it can either form this carbocation right here or this carbocation right here. So you can see that uh number one is generated more readily cause and is more stable than the carbocation too because the p orbital of the carbocation overlaps with the pi orbital of the benzene ring. And the positive charge is dispersed into the benzene ring, stabilizing it. Okay, and that is why when we have our chlorine and ion to act as a nucleophile to attack the positively charged carbon, we will end up forming X, which is this product. All right, next question. We can see that uh, draw labeled diagrams to illustrate the bonding in benzene to in terms of orbital overlap and show how different types of bonds are formed. So show how different types of bonds are formed, we need to form the sigma and pi bonds. And we also have to label the diagram. So label diagram means I would want to annotate. So the annotation is such, we have to elaborate that there's head-on overlap between the sp2 hybrid orbitals of carbon and s orbital of hydrogen to form the sigma bond, which is right over here. Okay, which is right over here. And then the head-on overlap between sp2 orbitals of carbon atoms to form the sigma bond over here. Okay, and the drawing I must see these two orbitals, sp2 and s orbital. Alright, and show how benzene is being formed. So the hexagonal ring. Alright, the next part to show is the pi bond. So to show the pi bond, this is how you show the pi bond. You show the sideway overlap of the p orbitals. Okay, and this forms the delocalized pi electron cloud. Okay, the next question explain the difference in reactivity of benzene and ethene towards BrCl. This question, we know that in my previous notes, in my previous video, I talk about benzene being less nucleophilic and less electron rich than alkenes. So as long as you give that reason, it should be totally fine. Um, Another part is due to the delocalization of pi electron cloud, the electron density of benzene is not high enough for the weak electrophile. So are you using your answer in A and answer in B? Remember, answer in A, we are not using a catalyst. And for the benzene group to undergo electrophilic substitution, it needs a harsher condition, which is the catalyst, to generate the stronger electrophile. Okay? So because I don't have a catalyst, and I don't have a catalyst, and alkenes are also nucleophilic, it can actually attack the electrophile also. So you can see based on the above part, the alkene, if you compare either the alkene and the benzene ring, I would say the benzene would more readily, sorry, the alkene would more readily attack the weaker electrophile, which is BrCl. Alright? And that is when uh not harsh conditions, milder conditions are being used. And how you use your structure of benzene in B, we see that focus on the concept of the delocalization of the pi electrons. Yeah, focus on the delocalization of pi electrons. Okay? Next up we'll look at is the RI paper. So the RI paper is somewhere all the way down. Okay. Alright, I'll go, because this is the answer sheet, I'll go back to the question paper. Okay, so in this case, I don't think you encountered this concept before. Aromaticity will have, there's many requirements to fulfill the concept of aromaticity of a compound. And that is these two criteria. Overlapping on continuous overlapping of the p orbitals, as well as for n plus 2 the localized pi electrons, where n is 0 or a positive integer. So based on the criteria above, we note that this compound below is actually aromatic. Consider the hybridization and explain how it satisfies both criteria. So take note that all of my carbon atoms are sp2 hybridized because you can see there's 3 bond pairs and 0 lone pairs, and by Vesper, this causes a trigonal planar geometry, and we relate the trigonal planar geometry to 3 sp2 hybrid orbitals and 1 unhybridized p orbital. Okay, so in total, we will see that there's 5 unhybridized p orbitals, including the negatively charged carbon right there. And all of them sideway overlap to cause delocalization of pi electrons. So my criteria 1 is fulfilled. They are continuously overlapping p orbitals. Then second is to find out how many pi electrons are there. So note that every single bond represents 2 electrons. So we have 2 pi, and the negative charge over here, there's actually 2 more electrons. So if you can see, if I draw out the structure, there's actually 2 more here. Okay, so that so if you look back at the answer sheet, can see that there's a ring of 5 sp2 hybridized orbitals. Sorry, hybridized carbon atoms. And each has an unhybridized p orbital that overlaps continuously. So what I want you to focus right here is that um you notice that we have these two criterias. You make sure these two criterias you copy and paste or modify copy and paste these keywords into your answer. Okay, so you have to make use of the information uh in the question to answer the question fully. Okay, overlaps continuously, and the negative charged carbon contains a lone pair of electrons in its unhybridized p orbital. Together with the 4 pi electrons of the 2 CC double bond, there's a total of 6 delocalized pi electrons. So you can see the answer clearly shows the two criteria being fulfilled. Okay, the second part of the question shows uh, why it undergoes substitution reaction instead of addition reaction for the compound below. So given that this is aromatic, we need to show that this fulfills the two criteria. So have to explain that because all 10 carbons are actually sp2 hybridized with an unhybridized p orbital that sideway overlap continuously. That is criteria 1 to show that it's aromatic. And second, there is a total of 10 pi electrons that are delocalized. So because of this aromaticity, it undergoes substitution to prevent the loss of aromatic stability, or in a sense, retains its resonance stability. Okay, so let's look at the answer. The product retains its aromaticity as there are 10 delocalized electrons in the continuously overlapping p orbitals. And if we undergo addition reaction, it will no longer be aromatic due to the absence of continuously overlapping p orbitals. So note that in your answer, you must compare substitution with addition reaction as well as use info from question. Okay, now I'll go on to the next part. Alright, so this is a unusual reaction that you won't see in the textbooks. In reaction 1, oleum is being used as a reagent to convert methyl benzene into compound A. Oleum is a concentrated solution of sulfur trioxide in sulfuric acid. Reaction 1 involves these steps. So when information is given, please read it carefully so that you can answer the next few questions. So form a balance equation for the formation of HSO3 plus. So SO3 plus H2SO4, and it will give you HSO3 plus and HSO4 minus. So just play around with the atoms and it will give you this answer. Okay? Give a reversible arrow also because you're forming the electrophile. Okay? Usually the first step of an electrophilic substitution, we will represent it with a reversible arrow. Okay? Then the next step, describe the two-step electrophilic substitution mechanism. Okay? So in this case, resulting in the formation of A and regeneration of H2SO4. So in this case, this is somewhat similar to nitration. So let's take a look at the reaction here. HSO3, we see that the sulfur is the one that is being attacked because sulfur is less electronegative than oxygen. That's one. It also have the energetically accessible vacant orbitals, so it can also act as the Lewis acid right here. But I would say the more important reason is that it's electrophilic. Okay? And you can see the hydrogen cation is being uh, pushed out. And what I mean by pushed out, actually a better answer I would say is you use the lone pairs on the oxygen of HSO4 and you gain the proton so that you form the final product below, which is this one. Alright, next question. Suggest the reagents and condition for reaction 2. Okay, so this is a nitration reaction, so just uh remember your reagents and condition properly. YB is formed in greater proportions compared to C. So this we have two activating groups. What this question is suggesting to you is that NH2 is a stronger activating group. Okay? So why is NH2 a stronger activating group? Is one reason you can possibly look at if you visualize the thing is that nitrogen is less electronegative than oxygen. So what it suggests? That suggests that uh the electron density uh of benzene ring, yeah, it can also reduce to a smaller extent by NH2. So that is why we can also think about it as and nitrogen and carbon having similarly sized orbitals. And thus the extent of delocalization of the extent of delocalization of the lone pair of electrons on nitrogen is much greater compared to oxygen. So I repeat that again. So basically, this lone pair of nitrogen will more readily be delocalized compared to the lone pair on oxygen, and that is because nitrogen is less electronegative than oxygen and withdraws electron density to a smaller extent compared to oxygen. So let's look at the answer. Nitrogen is less electronegative and its lone pair of electron is more readily delocalized and more activating. Okay? Okay, the next few questions I would say are more manageable, so I guess I'll leave this next few question up for you uh to see the answer. If you have any questions regarding Arenes, you do feel free to message me about it.